One of the biggest leaps forwards in our understanding of chemistry came from atomic theory. Atomic theory was first postulated in about 500 BC by a scientist or a philosopher called Democritus. And Democritus basically had this idea that everything around us was made of these uncuttable particles, which he called atomos, okay, which you might recognize the root of the current word atom, I should say. And the only reason we know about this is because people made fun of Democritus's ideas, and they said that clearly that must be crazy, because you can keep tearing, something like a bit of paper into half, into a quarter, into an eighth, and clearly you can keep tearing it into an infinite number of pieces, so therefore atomos can't be real. There's no such thing as atoms. And the matter sort of, no pun intended, sort of lay dormant for a while until about 1800 AD, when an English chemist called John Dalton came up with the idea again and noticed that it explained an awful lot of observations that were being made at the time. And so in John Dalton's world, then matter was made of atoms themselves, and atoms of a given element were different from atoms of another element. So atoms of one element were different than atoms of another element. So what that's like saying is that lead atoms, so I'll write a lead atom as Pb in a circle, are somehow different than, say, gold atoms, which I'll write as Au inside a circle. And that seems relatively obvious to us now. But remember, if you look at something like bricks, all the bricks are identical maybe in your house, and all the bricks in your neighbor house might be identical, but the way you arrange the bricks controls the shape and the design of the house, and so it was perhaps thought that the atoms themselves were looped together in rings, or circles, or squares, or triangles, and that's what made one element different from another. So Dalton's idea was that all atoms of a given element were absolutely identical. The big help, or the big leap forward here, was this help to understand compounds. So we said earlier that compounds were always consistent of two or more elements in a fixed ratio. And why does this help us understand what compounds are? Well, we can see that if you have something like carbon dioxide is made up of a single atom of carbon bonded to two atoms of oxygen, whereas something like carbon monoxide is a single atom of carbon bonded to a single atom of oxygen. And clearly the atoms have to bind in whole number ratios, and that means that the weights of the elements have to be present in whole number ratios too. It's impossible to have a carbon dioxide with 2.2 atoms of oxygen and, say, 1.2 atoms of carbon. They always have to be in fixed whole number ratios. If we look at something like water, water is composed of two hydrogens bonded to one oxygen, whereas hydrogen peroxide is composed of two atoms of oxygen bonded to two atoms of hydrogen. And again, these are in fixed whole number ratios, so that implies that the water molecules always have that same ratio of hydrogen to oxygen. So does peroxide, and so each atom presumably has a separate weight, so that means that weight ratios will also be fixed. And lastly, we can understand what's going on in the chemical reaction. So it turns out in a chemical reaction, so all we really are doing is shuffling around the bonding of the atoms. So we're just shuffling around atoms, which is crazy to think about it. I mean, the thing that keeps us alive is obviously eating and breathing, and what we're doing is we're taking the atoms in our food and in the air, and we're shuffling them around. We're incorporating them in our body, and then every day we remove some atoms from our body, and this is all that's going on. If you take a reaction between hydrogen and oxygen burn in a fairly explosive reaction to produce a large cloud of water vapor. And what's going on here is that the hydrogen molecules are composed of pairs of hydrogen atoms. And I'm going to balance this. We'll talk about balancing later. And oxygen is also composed of pairs of oxygen atoms. And they recombine and they form water, which is composed of a ratio of two hydrogens to one oxygen. And in order to keep the number of atoms of each element the same on each side, I've got to do it like so. So all we're really doing is we're taking these six atoms and we're shuffling them up, and instead of having them bonded the same way, we're rebonding them and producing water molecules. So that dramatic explosion when you burn hydrogen is really none other than sort of like one of these oxygens going in between here and one going in between here. We're just shuffling things around.